Dora, 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 the Explorer. Dora, boost that super cool exploradora. Need your help? Grab your backpacks. Let's go. Jump in, vamonos. You can lead the way. Hey, hey. Do Dora, do Dora, do Dora, do Dora. Swiping, no swiping. Swiping, no swiping. Aw, man.
Hola everyone, I'm Dora, and this is Boots.
I'm Boots.
Today I really need your help. I'm trying to further my studies and get into grad school to study chemistry, but I'm really struggling with acid-base chemistry.
It's very hard.
You can't memorize your way through it, you have to actually understand the concepts.
No memorizing.
As my abuela would say, no puedes memorizártelo.
Good old abuela.
But I know we can do this, so let's check out Map and see what he has to say.
I'm the map. Hola, amiga. The first thing you need to know about acid-base chemistry is that when determining which compound is a stronger acid or base, you have to consider the stability of the conjugate. The conjugate is a resulting compound after an acid has been deprotonated or a base has been protonated. Keep that in mind during your travels to grad school. A conjugate is most stable when it's next to particular groups, depending on whether or not you're looking at a conjugate acid or a conjugate base. For a conjugate acid, it's more stable if it's next to electron-donating groups because they would have just been protonated, and there's likely a resulting positive charge. This atom holding the newly added proton is more stable if the positive addition or potential charge can be satisfied via the inductive effects of electron-donating groups. These groups inductively donate a negative charge, which better stabilizes the resulting positive charge. For a conjugate base, it's more stable if next to electron withdrawing groups because it would have just been deprotonated and there's likely a possible negative charge. These neighboring groups delocalize the resulting negative charge by sucking away some of the electron density, which makes it more stable. But you have to be careful because lone pairs can be donated even if they are on electronegative atoms, which would be unfavorable to a resulting negative charge. Don't worry, there's more. You also need to keep in mind resonance when determining which conjugate is more stable. As a rule, resulting negative or positive charges are stabilized when there are different resonance forms for the molecule to make. For example, the combination of lone pairs next to a conjugated pi system makes for great stability. The electrons are able to shuffle around and can either donate to the resulting positive charge or withdraw from the resulting negative charge. And the last tip is to consider the electronegativity and the size of the atom that is being protonated or deprotonated. As a rule, if the atom is more electronegative, it will better accept a negative charge. It will be easier deprotonated than an atom that is less electronegative because it is greedier with its electrons. With size, a bigger atom is more able to sustain whatever resulting charge comes from the action. A good strategy to follow when trying to solve these problems is the Burt and Ernie method. When comparing two molecules and trying to see which is the stronger acid or base, first look to see what is different between the two molecules, and then determine what about these differences would make one better than the other, or which one will have the most stable conjugate. Your first stop is Davidson College Union.
Sounds great. Off to the Union we go.
Sounds good.
Come on, vamonos.
Everybody, let's go.
Dora the Explorer!
Swiper!
You think you make it to graduate school, but you'll never solve these problems. The only way to get into Union is to pick the door with the least acidic molecule on it. Ha 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 ha!
Boots, I need your help.
Hey, I'm happy to help, Dora. No problem at all. So let's look and see what we have here. So from the looks of it, it looks like these two molecules are pretty acidic because they're pretty electron withdrawing and there are no lone pairs around that could donate, which could make it less acidic. So we're going to go ahead and eliminate these two because, again, there are no lone pairs anywhere. Whereas these two have lone pairs. So we just need to decide now. We both know that they're electron donating. We just need to decide which one is more electron donating because that makes it the least acidic. It's pretty confusing, but we got it, Dora. It's fine. So this one has lone pairs on the oxygen. So oxygen, and then we have a nitrogen that also has lone pairs. So how would you decide? Well, you have to pick which one is the least electronegative because that means they're going to be more willing to donate their lone pairs. So if you look at it, nitrogen is less electronegative than oxygen, which means nitrogen will just say, hey, you can have my electrons, we're gonna donate them, I'm gonna be the least acidic. So we should definitely go in this door.
That makes so much sense. This one is clearly the least acidic. Let's go in. Swiper, no swiping. Swiper, no swiping.
Aw, man.
Awesome job, Boots. Now let's check Map and see what we have to do next.
I'm the map. I'm the map. I'm the map. Hey, Dora. Great job on the last problem. The next place you need to go is the library. But before you head out there, let me give you some more tips for solving acid-base problems. Another thing to consider when determining which molecule would be the most acidic or basic is aromaticity. It's never electronically favorable to break up aromaticity or aromatic rings, so you should try to avoid that at all costs. Also, when picking which molecule is the most acidic or basic, you should consider how strained the system is. As a rule, if a system is more strained, it will be more reactive, which you should consider when looking at these problems. Now off to the library!
Okay, Boots, so just to recap on aromaticity, we have to have molecules that have an sp2 trigonal planar configuration.
Check.
They have to have 4n plus 2 pi electrons.
Check.
And they have to be conjugated, correct?
Sounds perfect to me.
Awesome.
Dora the Explorer! Quick, answer these questions or you can't go in the library. Which one's more acidic?
Oh, Swiper, that's so easy. We just learned
What a
that.
coincidence!
The most acidic one is going to be the one with the methyl group because when you deprotonate it, you're not breaking the aromaticity.
Boom!
Rats. Well, what about this one?
Oh, she's got another.
Oh, it's also...
This one's the strained system, Dora. Don't forget.
Oh, yes, strain system. So which one's going to be more acidic and react the faster? The one that wants to release that strain. So the square wants to... Since it has 4-membered rings, it wants to release the strain when it's deprotonated.
The cyclobutyl.
Aw, man.
Swiper, no swiping. Swiper, no swiping.
Come on, vamonos!
Everybody, let's... Swiper!
Ha ha ha! Dora the Explorer, we meet again. More problems to make you fail. But this time, we're going to race. And if I go faster than you or get more right answers than you, then I'll take your map and you'll never pass.
So what are we doing, Swiper?
We get to pick the most acidic molecule.
All right, we can do it, Dora.
We
It's
can
fine.
do it.
We can do it.
Ready, set, go!
Done.
Okay.
Let's see your answers, Swiper.
No, let's see your answers.
Okay, we'll explain our answers too. For number 1, if we use the Burt and Ernie method, we see that the main difference is the oxygen and the sulfur of each molecule. So, when we deprotonate both oxygens in both molecules, there's a negative charge. And what can better stabilize the negative charge? Well, obviously the most electronegative atom, because it can pull electron density towards it. For number 2, what's the main difference between these molecules? Well, the atoms that are being deprotonated, one is an oxygen and one is a sulfur. In this case, we have to find the biggest atom because sulfur has a bigger area that can better delocalize the negative charge. So B is the most acidic. Boots, for number 3, I picked B because I know it's a carboxylic acid, but can you further explain why it's more acidic?
That was a great pick, Dora. Carboxylic acid was the correct pick. Very smart. But also, it's an even better pick because B has further resonance than A. So B, when that oxygen gets deprotonated, there's a resulting negative charge, and the lone pairs can flip over and make a double bond, and then that double bond can flip up, and it stabilizes the negative charge because it's delocalized between the whole sort of molecule. And then for A, you're tempted to pick A because there's an aromatic ring that is electron withdrawing, and the carbonyl is pretty electron withdrawing, and so you're like, oh, we learned that electron withdrawing is good. But in reality, for A, you can't deprotonate from the ring because it's aromatic, and if you deprotonated, that would break up aromaticity, which is really unfavorable. So you have to deprotonate from the aldehyde, and that does not have as much resonance stabilization as B does. So B is definitely the right pick.
Thanks, Boots. For number 4, we got different answers.
Yeah, but you're wrong. It's a trick question. They're both the same.
If you look at the double bonds, the positioning is different. In this molecule, whether you deprotonate from this side or this side, then you have resonance and it can just go around the entire molecule. Instead, for letter B, you have a little bit of resonance because if you deprotonate here, then this double bond can move here, but then you get stuck. So
Because
that's why
it's not conjugated.
it's not conjugated. That's why A is more acidic.
Swiper, no swiping.
Aw, man.
That was awesome, Dora. Nice job. What's up next?
I don't know, Boots. Let's check map.
Head over to Wall. You can do it. Last stop. Good luck, Dora.
Vamonos! Everybody, let's go!
Dora the Explorer, I finally got you. You'll never get this question right and you'll never make it to graduate school. This is your last problem. You have to rank the nitrogens in order of basicity, from least basic to most basic. You'll never get it. Ha 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 ha!
Okay, Boots. let's rank these in order from least basic to most basic. We'll think about it and you can explain them.
Okay, Dora, sounds great. Okay, so least basic, we're looking for electron withdrawing group. So let's see, what do we have here that is electron withdrawing? So we see we have this huge electron withdrawing group right here, which is going to make NC the least basic because it's going to suck the electrons away, which does not help stabilize this resulting charge. So then, the next least basic would be NB, because NB is next to this carbonyl. And I'm not going to lie to you, that carbonyl, pretty electron withdrawing. It's going to suck your electrons away. Sorry about it. Then, after that, the next least basic is, is that an A? NA, yes, NA.
Yes.
And that's because this is next to this electronegative nitrogen. So even though it's not as electron withdrawing as the carbonyl or this group right here, it's still electronegative. So we can't really discount that. So far we have NC is the least, then we have this one, then NA.
Which means that the most basic
Yes,
would
exactly.
be ND.
ND, and why is that, Dora?
Because it's next to an electron donating group.
Yes, we have the inductive effects of these electron donating groups. And that is really what we want for most basic. So we got it, Dora.
Aw, man.
Awesome, Boots. Now I know that I can get into grad school.
We did it!
Lo hicimos.
We did it!
Dora, 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 the explorer. Dora, who's that super cool exploradora? Need your help? Grab your backpacks. Let's go. Jump in, vamonos. You can lead the way. Hey, hey. Do Dora, do Dora, do Dora, do Dora. Swiping, no swiping. Swiping, no swiping. Aw, man.